Welcome back to Chapter 2 in Statistics. This chapter, we're actually going to get into a little bit of numbers and graphs and stuff. So, believe it or not, that probably actually sounds like a little bit of a breath of fresh air to some of you guys. So today we're going to be looking at displaying and describing categorical data. So we're specifically looking at categorical data. The next chapter we'll start looking at quantitative data because we do graph them differently and we deal with them differently. So we're going to look at them separately. Some of the things that we see today will be for just any kind of graph, like it's a universal thing, but a lot of it is specifically for categorical. So our learning targets today, my first learning target is to remember to set the learning targets to fade in when I want them to, instead of just appearing all at once. But we're going to analyze given bar charts and pie charts. We're going to analyze given frequency tables and contingency tables, create and analyze relative frequency distributions, create appropriate displays for categorical data, and use frequency tables to compare distributions. So, as you're reading the book, which you need to be doing, you'll see each of these just basically in order right through the book. And it does a good job of explaining each of them. I'm going to go through the main points here, but again, the book has more detail than I can give you in a short lesson, unless you want a short lesson to take an hour or an hour and a half. And I know I don't want to be listening to me for that long, and so I can't imagine you would either. So our first point, the 3 rules of data analysis. Now this goes for categorical or quantitative. These are important. The very first thing you want to do is you want to make a picture. When you're just looking at data or even data tables, it's really hard to see what's happening. Make a picture. And by a picture, generally here, it would be a good graph, an appropriate graph, a good graph. And what that's going to do is it is going to allow you to think about the data that you're looking at. Like, it'll allow you to think about it in different ways. The second thing you're going to do is make a picture. When you make a picture, it's going to show you things that that it won't see in just the data or the tables. And in fact, different kinds of pictures, graphs, will show you different things. So depending on what you want to see, you make different graphs. And sometimes when I get data, it's usually a quantitative data. I make a histogram and a bar graph because you see different things from each of them. And so it gives you a better overall look at what you're working with. And so we make a picture because that is going to show us what we're doing. And the third rule of data analysis, can you guess what this one's going to be? If you said make a picture, yes, making a picture will help you tell others about your data. Graphs and pictures are way more communicative. They communicate a lot more things than just numbers and tables and stuff. You can get a good overall picture. They can be more persuasive if you're trying to persuade someone of something. And depending on the graph you use, you can show different things that you're trying to highlight. And there are various different types of graphs. We'll be looking at some, but there's other types of graphs that have their place but aren't like, the big name ones. And they will show different things. And so when you're creating your graphs, when you're creating your pictures, it's important to know what it is that you're trying to communicate and to do it appropriately. There's a few pitfalls as well. One type of a good illustration comes straight from your book, straight from your reading. It's these two graphs right here, these two graphs are using the exact same data. And it's from the 2016 electoral vote for president. The top one is just showing like geographically what states went for what candidates. However, some states are big with very few people, and some states are small with a lot of people. So the electoral vote doesn't necessarily match this picture of the geography. The second one, the bottom one, uses the same data. You can see that it's kind of United States shaped, but in this one, each electoral vote gets one box. So now the states are sized based on the number of electoral votes they get. These two graphs tell the story of the same data in different ways. One of them isn't misleading or the other one's not misleading. It's just, what are we looking at when we're looking at our graph? Now, if you want something that can be misleading, using pictures and using colors and using things, that can be very difficult to do right. Example, and this is also right from your book, we have the, they're talking about the Titanic during this section. As you're reading, you'll be able, like, that's where they're getting all their examples and the percent of people that died or survived, and the number of people. And so here, they use a picture. They use a picture of the Titanic. The problem is that right here, we have like about 300 deaths. And right here, we have about 900 deaths. And this is fine. But the problem is the pictures. When they enlarge the ships, like this one is only this tall, but this one, it enlarges 3 times wide, but it also enlarges 3 times tall. And so it looks huge compared to the small one, because the area did not increase by 3, the area increased by 9. So it actually looks 9 times bigger. And we want to avoid that. And this is called the area principle. We want the areas to represent what they're supposed to represent. And so if you can extend the picture just horizontally, in this case, or possibly vertically, if your bar graphs are going vertical, then that would work out okay. But by expanding it both horizontally and vertically, it got much bigger than it should have been. And so it becomes misleading. It looks like the crew had way more. I mean, they did have way more deaths, but it looks like it was way more than it even was. And so that's something you just want to be careful about. Also, when you're looking at graphs, be careful about that kind of thing. Because remember, there are people out there that get paid money to mislead you by using statistics. So, the next thing we're going to look at is frequency tables. How do we put data, categorical data, and change it into numeric data? Well, it's pretty easy. We just count how many times does each category happen, and that becomes a frequency table. So here I have color. It could be favorite color, could be color of your eyes. I mean, it's during school, it might be early in the morning. You might have red eyes, I don't know. How late were you staying up working, reading your textbook? Except you'd probably read that after listening to this, hopefully. But it's just color. Like, you can make it whatever you want. It could be color of favorite color of ketchup. We have colored ketchup now. What's your favorite color of ketchup? And these are the frequencies. I asked 25 people. 3 of them said blue, 6 of them said green, 10 said red, 2 said purple, 4 said yellow. And so that's a frequency table. You've made these before. We can change these into a bar graph. Now with a bar graph, I mentioned be wary of the use of color. In this case, the use of color in the bar actually makes sense, because each bar is its color. When I first put this on here, actually we have a pie graph later on. This was all blue, and it was very boring. This doesn't mislead it, and it's less boring. But when I put the pie graph on, the pie graph can't all be the same color. That doesn't work out in seeing the different pieces of pie. But the colors were vastly different than what they said they were. That would be very misleading. And so I changed it, as you'll see, so that the colors are what they're supposed to be, which helps it to be less misleading. So when looking at this bar graph, there's a few things to notice. One, the graph is labeled. Up here, it's just color. It's probably favorite color. Or no, it's color of ketchup. That's what we decided. The categories are all labeled on the bottom. Usually the side would be labeled frequency. Although with a bar graph like this, each one counts as one, and it's that one is a little bit obvious, and so it doesn't always have to be labeled, but it's good practice to label it, because as soon as you deviate from that, you really do need to have it labeled. And then one thing to notice about bar graphs, the bars are not touching. They are all separated, and they are centered on the category. And those two things are important. In the next chapter, we're going to learn about histograms, which is something you've already learned about. And those are they're not the same. Like histograms, the bars are touching, and they go in between the different values. So those are bar graphs. Notice each bar is the same width as well. And so that's frequency. We could change this into relative frequency if we wanted to. Relative frequency, we just take each of our frequency numbers and divide by the total. The total was 25. So we'd go 3 divided by 25, 6 divided by 25, 10 divided by 25, etc. to get the relative frequency. Now this would be a percentage. We'd have 12% preferred blue ketchup, 24% preferred green ketchup. Relative frequency can be useful because it gives more of a picture of the whole. When we just say, oh, 3 like blue, 6 like green, it's like, yes, but how many? But percentages, we know how to decipher percentages. Also, when we start comparing different things, or if we want to generalize to a population, a percentage is good. I mean, let's say I took this class and it had 25 people in it. I got your opinion. And then I went to the band class with 75 people and I got their opinion. The numbers are not going to be comparable at all because they're all just going to be off. But the frequency, the relative frequency, the percentage is going to still be consistent. That's something that you can look at and compare even when the population or sample sizes are different. The graph of this is a bar graph and it looks identical. The only difference is the y-axis. It's now percentages, or I left them in decimal form instead of the numbers. And this one you'd want to label relative frequency. But like it is identical to the point where we could go back over to this original graph and we could just make this 12 over 25, 10 over 25, 8 over 25, all the way down, and it becomes the relative frequency graph. There is no other change to this. Another graph that we use when trying to look at categorical variables, especially when we're looking at parts of a whole, as I mentioned, is that pie graph. So here we have our favorite color of ketchup in pie form. It's basically a relative frequency because it shows you the percent of the whole. I have it labeled with the frequency. I've seen it labeled with either. It doesn't matter that much, generally speaking. There's a key telling us what's what. In this case, it's color, so that doesn't really make much of a difference because the colors are labeled and accurate. But this is another way that we can make a picture for categorical data. The next piece we're going to look at is a contingency table. A contingency table comes when there might be a few different variables that we're looking at. The book is using the survival rate on people that are alive and dead and the class that they're in. I'm going with the education level of people and their age. So in this, we have every individual fits into exactly one space. You're not going to both have 4 more years of college and be from 25 to 34, and have 4 more years of college and be from 35 to 30 or to 54. It's going to be one or the other. So you only fit into one of these boxes. Now from here, this is called a marginal distribution because we use the margins, the totals. It has the contingency table has the totals in it, and that's going to be important for what we're going to do. This can tell us a lot of data, and one of the problems or one of the issues that people sometimes have is they don't read the question carefully. They don't see exactly what they're looking for because some of these things will look very, very similar but mean different things. And so we're going to go through a series that are actually fairly similar and mean different things. So the first one, what percentage of the population completed high school? This one's a fairly basic one. We just have everyone who's completed high school, which would be this group, divided by the total population. So it's going to be 58,087 divided by 175, 230. And then you can use a calculator, calculate that out. You wouldn't do that in your head. That would be a bit ridiculous. But you can find the percentage there. It's just the total divided by the total. And that's the completed high school. Well, what about the percentage of the population that's between 35 and 54? So now we're looking at all the 35 and 54-year-olds. So it's going to be that divided by our total. So now we're looking at 81,435 divided by the 175,230. So that would be the percentage of the population that's in between 35 and 54. All right, that's not too bad so far. It's the next ones. I'm going to be writing on that graph more, so that's why I erased those. What percentage of 35 to 54-year-olds completed high school? So now our population here is the 35 to 54-year-olds. That's all we're concerned about right now. We're just looking at this group. All the rest of it doesn't matter. So we want how many of them completed high school. That's that amount out of the total. So that's going to be 26481 over 81435. The next one, what percentage of people who only completed high school are between 35 and 54? So now, I'll just switch up colors here. Now we're just looking at the people that completed high school. Like, we're not concerned about the people with college education or the people without that high school diploma. This is our whole population. And so that's still the amount that did it divided by that many total. 26481 over 58087. So these two questions, these last two that we did, look very, very similar. Getting them mixed up is one of the mistakes that people make more often than other things. The other piece we could do is what percent of the population completed high school and is between the 35 and 54. In this case, we're looking for the cell percentage. That would be that divided by the total, 26481 over 175230. And sometimes it's asking for just one. Sometimes you actually make the table. Like you'll have this table and then you'll make another one, or extend the boxes a little bit so it's in the same spot. And you'll do all the row totals, or all the row percentages, or all the column percentages, or all the table percentages. This would be a table percentage because it's over the table. The row percentages was the ones that were over the rows, and the column percentages were the ones that were over the columns. And so sometimes you need all of them. And so you do it the same way. If we were doing all of these ones, we could have the 9155 divided by the 8143. We could have that. We could have this one divided by that. We could do these ones divided by that column total. We could do these ones divided by that column total. So you can do it for more than just one thing, depending on what the question is asking you. If you had to make a graph, the graphs for these are the exact same as the graphs for just the regular frequencies. You would just do it with each thing. And you would do one, like if we found all of them for the columns, we'd have a graph for the 25 to 34-year-olds. We'd have a graph for the 35 to 54-year-olds. We'd have a graph for the 55 pluses. And we'd put them next to each other. We make the scales the same so that we can compare them and see them. You can also do stacked bar graphs, which I didn't put a graph of one of those in here, but they show you a few in the book. So as you're doing your reading, you can see some stacked bar graphs. But that's what the conditional distributions are. Then the next thing is sometimes there is a difference, but is the difference actually meaningful? Is it big enough to actually matter, or was it just by a little bit of chance? The book talks about this a bit. We'll be talking about this a lot more later on in the year as well, because there's significant and there's statistically significant. Like, is it statistically significant? Is it big enough that it didn't just happen by chance? And so it's just kind of a cursory discussion here, but it's when things are really close, it's like, okay, yeah, that's just that random variation. But it's when things have big differences than what you would expect that it's important. And then don't forget to be looking at the what can go wrong stuff. Talks about the area principle, talks about misleading either the way you're doing graphs or the data that you're using. That don't confuse similar sounding percentages. That's what we're just talking about right in this area. Those sound a lot the same. Look at the variables separately. Use enough individuals. Here I had a group of 25. Depending on what we're doing, that might be okay. That might be too small of a group to really do anything. I do love their example though. When you're reading it, their example was, we found that 66.67% of the rats improved their performance with training. The other rat died. Like that, 3 rats is not enough. I mean, that rat that died, like, why? What? Like, did it have anything to do with the training, or did it just randomly die and it would have been trained? You don't know. Then don't overstate your case. And then finally, Simpsons Paradox. I know that personally, I've always wanted to have a house on a lake, and I would build one dock into the lake, and then right next to it, I would build a dock that looks the same, and I'd put a big sign across that says Swanson's Paradox. But I cannot afford a house on the lake, much less one dock. But what Simpsons Paradox is it's a phenomena that when looking at data, it flips direction when you're looking at like the combined data versus when you split it up. It gives a couple examples in the book. We're going to look at another one. So we have two baseball players during the first 2 weeks of the season. It's not this season. Don't try and look it up, and this might just be made up data. I don't know. But we're going to look at the at-bats. So player 1, in week 1, he had 2 hits out of 5 at-bats. So the batting average would be 2/5, which is 0.4. And week 2, he had 5 hits out of 20 at-bats. So we have 5/20, which is 1/4, which is 0.25. Player 2, first week, had 9 hits out of 25 at-bats. So that would be 9/25, or 0.36. And week 2, he had 1 hit out of 5 at-bats. So that would be 1/5, or 0.2. So looking at this data, which batter had the better batting average? Well, week 1, player 1 did better. Week 2, player 1 did better again. So player 1 is obviously the better batter. However, if we combine and take their total, we're going to have 7 out of 25 at-bats, which is 0.28. And here we're going to have 30 at-bats, and we're going to have 10. Oop, that slipped. So 10 over 30 is 0.33, whatever. Player 2 had a better overall batting average, even though for each individual week, player 1 did. And that has to do with just how the weeks broke up. Player 1 had, like, they were close, but with the few number of bats versus the bigger number of bats. In the book, it talks about Mo and Jill piloting and the day and the night. It's like, well, during the day, they're on time more often. And Mo did mostly day flights. Jill did at night flights. So yeah, she had more times when she was delayed. But overall, it went the other way. So that's Simpsons Paradox. It's kind of a weird thing, but that's what that phenomenon's talking about. So that would be the basics of Chapter 2. Again, be sure to read your book. There's stuff in there that I didn't talk about. I'm already up to almost half an hour. You don't want me talking about every single thing when it is a very readable book, and you can read it and get that explanation as well. But other than that, I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.